Hello, future scientists. I am Atom. Join me in this adventure where we explore how we can solve momentum conservation problems in a fun and easy way. So here's our first problem. There is a blue train car of mass 1000 kilogram and it's moving at a velocity of 4 meters per second. And there's also a red train car of mass 3000 kilogram at rest. These two train cars collide, and after collision, they're going to couple together and move together, and we have to find their combined velocity after collision. Let us first visualize this problem to make the process easier. What do I mean by that? As we read each sentence of the problem, we will create an image for it. Since I'm solving this problem on a computer, I'm going to use the computer images. But when you solve this in your notebook, you can do stick figures or you can do squares or circles to represent the objects. This will help you to really visualize the problem and not miss any detail. The next step is to write the givens next to each image that you have created. Givens is basically the data that is given to you in the question, because sometimes the data can get lost when it's mixed up with so many words. But when you put the givens next to the image, the problem becomes much more visual, easy to comprehend. As you write the given data next to each image, do not forget to put the units. So the next step is going to be to calculate the total momentum of the two train cars before collision. And in this case, the blue train car has momentum of 4000 kilogram meter per second, and the red train car has no momentum because it is at rest. And we also see that it is an inelastic collision, and momentum is conserved for both inelastic as well as elastic collisions. The next step is to figure out the total momentum after collision. Since momentum is conserved, the total momentum after collision is the same as the total momentum before collision. So it is still going to be plus 4000 kg meter per second. And the final step is to figure out the velocity of the two train cars moving together. So the velocity is momentum divided by mass. So the momentum is plus 4000 kilogram meter per second divided by, this time the mass becomes 4000 kilogram because the two train cars are moving together. So we have to add up both of their masses. So we get plus 1 meter per second. Here is our second problem. How much force do you have to apply to stop a skateboard of mass 6 kilogram that's moving at a velocity of 10 meters per second in 5 seconds? In this case, we are going to underline the keywords and write the variables right above those keywords. So we are going to put the letter F for force, M for mass, and T for time. Now, as you can see, I did a squiggly line under stop and under 10 meters per second. That's because this combination tells us that there is a change in velocity happening to the skateboard. The skateboard is currently doing a 10 meters per second, but its final velocity is going to be 0 meters per second. So the delta V is going to be negative 10 meters per second. Now, just by looking at the variables, we know that the formula we would have to use is Ft equals m delta v. All we have to do at this point is plug in the values and figure out our unknown, which is the force. Another thing that is important to do is write the units next to the numbers. For instance, you're going to put 5 seconds, 6 kilograms, negative 10 meters per second. So this way, you automatically know what the unit for the force is going to be. You can see the force calculated is negative 12 kilogram meter per second per second. From Newton's second law, F equals ma, we know that kilogram times meter per second is basically Newton. So 1 Newton equals 1 kilogram multiplied by 1 meter per second. So we can rewrite our answer in terms of Newton. So the force is negative 12 newtons. Now let's go to our third problem. A small car and a heavy truck get into a head-on collision. Compare the forces and impulses they exert on each other. Determine who has a bigger change in momentum. Also determine who has a bigger change in velocity. When you see a problem like this, always start from first principles. For instance, in this case, there are two objects. Immediately we know that Newton's third law is working here. So the car and the truck are going to push on each other with the same amount of force in opposite directions. And they're also going to push on each other for the same amount of time. Now, force times time is impulse, so which means they're both going to exert the same amount of impulse on each other, but in opposite direction. Now, impulse equals change in momentum. So the change in momentum for the car and the truck is going to be equal and opposite as well. The only difference is, since a car has a small mass, it's going to have a big change in velocity, and the truck has a big mass, therefore a small change in velocity. Here is problem number 4. A bowler throws a cricket ball of mass 0.16 kilogram to a batter with a velocity of 30 meters per second to the right. After being hit by the cricket bat, the ball has a velocity of 50 meters per second to the left. This video will help you to visualize the situation. Now, question A says, what is the initial momentum of the ball after the bowler threw it? So I have created an image for it. So you can see the bowler is throwing the ball. Ball's mass is shown right under the ball, and its velocity is also shown. So we can easily figure out its momentum using P equals mv. So 0.16 kilogram multiplied by the 30 meter per second gives us a plus 4.8 kilogram meter per second. And since the image is there and the numbers are there, the problem solving becomes super easy. Question B says, what is the final momentum of the ball after the batter hit it? You just watched a video clip of the batter hitting it, so you can visualize the situation. So in this case, we need to look at the ball going the other way. So which means its velocity is negative. Do not forget that. The negative sign is super important. So the momentum is going to be the mass of the cricket ball, which still is the same thing, times negative 50 meters per second, which equals negative 8 kilogram meter per second. You can actually do simple stick figures to visualize the situation. Question C says, what was the total impulse delivered to the ball from the batter? We can use the formula Ft equals delta mv. Since we do not know the force that was exerted on the ball, we have to figure this out using the delta mv part of the formula. Delta mv is the change in momentum, which is final momentum minus starting momentum. So that is negative 8 kilogram meter per second minus positive 4.8 kilogram meter per second. So we get negative 12.8 kilogram meter per second. So now we just rewrite this as impulse. Since impulse is made up of force and time, we write this as negative 12.8 Newton seconds. Question D says, assuming that the bat was in contact with the ball for 0.02 seconds, what was the force that the bat delivered to the ball? Since we calculated the impulse to be equal to negative 12.8 Newton seconds, all we have to do is divide this by the time, which is 0.02 seconds, and we get negative 640 newtons. Now let's go to our next question. It says, how are Newton's 3 laws of motion related to the study of momentum and momentum conservation? So we know momentum is inertia in motion, and which means it relates to Newton's first law of motion, which is law of inertia. We also know that an impulse, Ft, causes a change in momentum, delta mv. And Ft equals delta mv, we can simplify this as F equals ma by dividing on both sides by t. Like we get F equals m delta v over t, which is same as F equals ma, and that is Newton's second law, the law of acceleration. And finally, the law of conservation of momentum works between two objects, which is a system. So basically, law of conservation of momentum is an extension of Newton's third law. So all 3 Newton's laws of motion works with momentum, impulse equals change in momentum, and the law of conservation of momentum. Happy learning. Thank you.